Hello and welcome to this video on PyTorch linear logistic regression for classification. So in this video we're going to use some of the basic functionality that we've learned from PyTorch to implement a simple linear classification model with linear regression and logistic regression. So in this animation you can see here we've kind of got an animation of our model training using gradient descent to try and separate out two distinct groups, which is what we try to achieve in classification. We've got our x's and our dots. We have our decision boundary trying to fit between those 2 points and 2 groups to try and separate them the best we can. Hopefully you have some idea of regression and classification already, but we're going to go over some basics, and I just want to point out a few things just to make sure they're in front of mind. So the basic linear regression that you're probably at least familiar with is this sort of classic case you may have learned in school. We have some data points on some x v y plot, and we want to fit a line to those points. It's a straight line using whatever method we want, and we usually represent our line in this case as y equals mx plus c, where m and c are some parameters of our equation that we try and solve for. Right. In this case here, we have a one-dimensional input and a one-dimensional output, and we're plotting the input versus the output of our equation. One thing I want to point out is that this plot here, we're not plotting input versus output, we're plotting each of the dimensions of our data point. So each of our data points is two-dimensional, so it has 2 values associated with it. Right, whereas in this point here, we really only have one value. Maybe you could say x and y is a dimension of our data, so we have 2 dimensions here. But what we're trying to achieve in this linear regression is very different to what we're going to try to achieve in linear regression for classification. Right. So let's set up our problem for our classification case. So in general, in classification, what we're trying to do is split up our data into distinct categories or distinct chunks. We want our model to, at some stage, tell us which group this data point belongs to. Right? You might have pictures of cats and dogs, classic example, and you want our model to say cats for cats, dogs for dogs. Right? Right? We don't have some continuous variable like in y equals mx plus c. For every x value, we have some continuous value y. We might have some discrete value that our data point belongs to, some discrete category. In the case of this notebook, we're looking at binary classification, so it's either a 0 or a 1, or a true or a positive, right? So for a medical diagnosis, you can be diagnosed with having it or not having it, so cases like that. So the simplest case we're going to look at is, before we get into the notebook, is a one-dimensional classification. So let's assume instead of having a y for each data point, we have instead just a single value x and a group that it belongs to. So because our data x is one-dimensional, we try and represent it in the same way that we've represented the 2-dimensional data in the notebook. Because one-dimensional, we're going to put it on a simple number line. Right? We have our number line, and we're going to draw a whole bunch of data points on that line. Okay, right, and let's say that we've also got some other variable that just tells us what group each of these data points belongs to. So let's say all of these belong to the red category, and all of these ones belong to green. You can represent this in the same 2D plot, x versus y, where y is just the category. It can be 0 or 1, so you could say that all of these green data points are zeros, and all of these red ones are 1. And you can plot it out that way. But I'm going to plot it on this number line here. I think it's a bit easier for visualization, the point I'm trying to make. So what we want to do is we want our model somehow to give us basically a classification. And you might see that, well, it's pretty easy in this case. there's some value x that we can threshold on, and if it's greater than that value, it's a 1. If it's less than that value, it's a 0. But we want to be a bit more rigorous than just that. We don't want to just look at the graph. We want some way to automatically work out what that boundary is, that decision boundary, and we want some automated way to find it. So how can we do that? Well, we're familiar with, as I said before, y equals mx plus c, and this basic equation basically says our line, that line that I drew before, exists where you plug in an x value, and the y value will tell you the other y coordinate, right? Plug in an x value, and this equation will tell you what the y value is, such that that point lies on our line. Another way to represent a line is with the general line equation, and it's typically written like this: 0 equals, we're going to use omega, where omega 1 and omega 0 are the parameters. Right, and it's possible to rearrange this equation to get something that looks like y equals mx plus c. You can do that yourself. But what this equation tells us instead, in a similar manner to y equals mx plus c, but what this equation tells us is the line exists for values of x such that you plug them in this equation and you get 0. So again, here, it's not so much a line as a point on this 1D number line, but basically my model, my decision boundary exists where I plug in the value of x and that value returned by this equation is 0. Okay. In the two-dimensional case, such as this 2D plot here, again, this is dimension 0 versus dimension 1 of a single data point. This line exists basically wherever you plug in 2 values and you get 0. So that line exists for points that when you plug them into that equation, you get 0. Now you can plug in any other value into this equation and you'll get something that's not 0. Okay, and that value that you get is essentially the distance away from that line to that point. In our one-dimensional case, that value is essentially the distance between this decision boundary and that point. Right? So this data point here, it's equivalent to this distance here. Not exactly equal to it, but it's equivalent to that distance. Okay, that's all well and good, but how does this help us? Well, it not only tells us the distance away, but it also tells us which side of the decision boundary it's on. If it's on one side, we'll get a positive distance, and if it's on the other side, we'll get a negative distance. Right? If it's on the positive x side, we'll get a positive value. If it's on the negative x side, we'll get a negative value. So let's see this in action a bit. So let's assign some values on my plot here. So let's just say this is equal to 1, this is equal to 2 here. These values are greater than 2, these values are less than 1. I won't give them all values. But you can see that possible place for this decision boundary is 1.5. Okay. So it's 1.5. So how can we use this information to try and work out what our values of omega 0 and omega 1 are? Well, we can work out what value of x, right, gives us a value of 0 when plugged into this equation simply by just rearranging this equation. So we should get negative omega 1 divided by omega 0 is equal to that value of x. And we know that's 1.5 just by looking at our graph. You'll notice here that we've got one equation, right, but 2 variables. You might think we can't solve for this, but basically what this says is that we can pick any value of omega 1 and omega 0 so long as this relationship is true. So any value that negative omega 1 divided by omega 0 is equal to 1.5, right, as long as that relationship holds, will work in this case. So hopefully that makes sense. So we can pick, let's just say that omega 0 is equal to 1 for simplicity. Right? That means that omega 1 should therefore equal 1.5 or negative 1.5. Okay, so let's just construct our equation again. 0 equals 1, still write it in x, right, subtract 1.5. Okay, so let's see what happens when we plug in our values. So 2, plug in this equation, will give us 2, take 1.5, that's 0.5, it's a positive value. If I plug in my 1, or any value less, that's 1, subtract 1.5, that's negative 0.5. So we'll get a negative value. If you plug in any value less than that, you'll also get negative. So you can see with this equation, right, in this general form, the sign tells us which side of that boundary it's on, and the magnitude tells us how far away that value is. Okay, so once we've got this, we can basically threshold at 0 and say anything that's positive that comes out of this equation is a 1, anything that's negative is a 0, right? So that's sort of how it's going to work, and we can generalize this to higher and higher dimensions, right? For our 2-dimensional case, it'll be something like 0 equals omega 0 x 0 plus omega 1 x1 plus omega 2, right? And we still want this equation to satisfy. And this is our 2D decision boundary here, which we're going to be doing in this notebook. Now the question is, of course, how do we find these values of omega 1 and omega 0 if we are not allowed to look? I said we weren't allowed to look, and then we did look to work out what they could be. Well, we can use gradient descent. We could also use a closed form solution in order to work out what those values are. We're not doing that in this notebook, so we do that in an earlier Jupyter notebook with NumPy, the NumPy linear regression. But in this lab, we're going to use just gradient descent with our PyTorch examples. So one more thing before we jump into that is just pointing out, where are we? Pointing out that you can represent this simply in matrix form. Right? If I have x0, I represent this as a 2D matrix, and I'm putting a 1 here. Right? This should equal 0. I got a 1 by 3 multiplied by 3 by 1. We should get a 1 by 1 out. Technically, it's a matrix. Okay, and this is basically what our linear model in PyTorch is doing. Right, we've got 3 inputs and 1 output. So our weights, well, in PyTorch it'll be the other way around because we transpose first. We technically do ATX, where that's our weights, but don't worry about that too much. It's just notation. Okay. So we'll have a 3 by 1 input. Oh, 1 by 3. 3 by 1. Okay. But PyTorch actually treats this last parameter here as the bias term. And so it's actually going to be to erase that properly, a 1 by 2 and a 2 by 1. And we also add on to as our 1 by 1 at the end. So that's how PyTorch does the same thing, basically. Okay, so this is just our linear regression for classification. So what we're going to do is we label half of our data as a 0 and half as a 1, and we regress using this equation. So the objective that we're going to use and try and minimize is that the distance basically between the output here, this isn't necessarily going to be 0. This is going to be some output. I'm going to call it, let's call it y, sure, y hat, or the predicted output. And we have some true value y, let's say it's equal to It's either equal to 1 or 0. And we're going to use a mean squared error to find the loss, and we're going to use backpropagation and gradient descent to update those parameters until we find some optimal solution. Right. I go through the derivation of the gradients by hand in the Jupyter Notebook in the NumPy ML section. In the linear regression there, you can see how you can actually calculate the gradients for those parameters by hand. But as we've already gone through how to use PyTorch AutoGrad, we don't need to do that because we now have PyTorch to do it for us. So here's our data. It's called the 2 moons dataset. You can see we've basically got these 2 concave groups that are sort of overlapping, and these groups are not linearly separable. What that means is that we cannot perfectly separate the 2 groups by our line, but there is still some optimal solution that we sort of classify the most points correctly. Unlike the NumPy ML example, we don't need to add those additional ones that we put here because PyTorch treats that differently, treats it as a bias, so we don't need to add that extra ones in our input vector. So you can see we do have that calculation for the actual loss and the actual derivative as well, but we don't need those, so I'm not going to go through that in too much detail. If you're unfamiliar with gradient descent, I've got a stat quest video here that's pretty good. That goes through a lot of the detail of how we're going to do this. I do talk about it a bit in the previous videos as well, but we're going to skip all that now. So the first thing to do is to define our single linear model. Our model, like I said, is just 2 inputs and 1 output. So PyTorch will define those 2 parameters for our weights, but it'll also define the bias. So we'll have 3 parameters of our model. We're going to use the PyTorch MS loss function, and we also need to define our optimizer. These are relatively high learning rate of 0.1, and we're going to pass the parameters of our linear model into that. So again, we're just following the very basic format that I introduced in the previous video of the series. We have a forward pass of our model we need to do. We have a loss calculation, 0 grad, loss by propagation, and optimizer step to actually optimize our model. So let's have a look at what we're going to do here. To define the max number of epochs, in this case, we're still just performing gradient descent. We haven't got into stochastic gradient descent yet. We're passing the entire training set of our to our model at each time and calculating the gradient given the entire data set. The epochs just tell us, just defines how many iterations over the entire data set we do. When we get to batch gradient descent, stochastic gradient descent, we're going to start breaking up that data set into smaller linear batches, but we'll see that in a later video. The first thing I do is I'm just going to calculate the accuracy of our test set. So we've got a training and test split. I'll go over why that's important in a future video, but basically we want some hidden or unseen data to actually test on to avoid problems with overfitting. So I'm going to do that first, just so we get a sort of baseline accuracy of our random model first. And I'm going to do that in this Torch NoGrad block that I introduced in previous videos as well. So PyTorch won't calculate or won't keep track of any gradients in this section here. I'll pass the test set, get our predictions out. Basically, I'm going to threshold it. I'm thresholding at 0.5, not 0, because again, what we're trying to do is we're trying to find a decision boundary between the 2 points. And because I'm training this model such that the distance between the decision boundary, my points is 0 for one and 1 for the other, what you'll expect is that this decision boundary won't potentially be exactly in between the points. It could be sort of closer. So if this is 0 here, that decision boundary should sort of sit in the middle, but still be sort of 1 away. So it might be actually pulled close to this side of the group, but you could have the case where the decision boundary kind of sits here, right? Not quite exactly 0 away, but not quite exactly 1 away. So we want to put that decision boundary in between the two. So we've got our, you can think of it as our actually model, where that line sits, but also how far away from that line do we want to define the point or the distance where we say it's now a 1, right? So our model says 0 for these points on average, 1 on these points for average. At what point, right? Because we've got this hard line of going from 0 to 1, at what point, what actual raw value from our model do we want to say we've transitioned from a 0 to a 1? The easiest place to put that is halfway between 0.5. So if the output of our model is greater than 0.5, that'll give us a 1, convert that to a float, to an actual number, so we can perform an accuracy calculation. So this will give us a 0 or a 1 for every test value, and we're just comparing that against the actual true test values, and we're summing that together, dividing by the total number to give us an accuracy. Right, that's just our accuracy calculation. The actual training step. So, here, again, there's our 5 steps. So, like I introduced in the last video, we've got 5 main steps. We do our forward pass of our model with our data, we get our output, and we use that to calculate our loss, the outputs, and our ground truth values. We've got our loss. We then zero the gradients, right, to remove any gradients that may exist from previous steps. And then we do our backpropagation. Backpropagating, calculating the new gradients for this particular loss, and then we tell our optimizer to perform 1 step of gradient descent. The same 5 steps that we talked about in the last video. We're also going to log the loss, so we can plot that out. That happens pretty quickly. It's a very simple model, and PyTorch is generally pretty fast, even when it's trained on the CPU, even compared to NumPy, or using NumPy arrays. So as we can see, we've got a pretty decent accuracy, 88.5%. As I said, we're not going to get a perfect accuracy because this data is not linearly separable. We would have to use non-linear models in order to get a better accuracy. But you can see our accuracy increases and converges, and so does our loss. It decreases and converges. Okay, so this is very basic introduction to how you can perform classification with a linear model in PyTorch. This is a very toy example, and it might get a lot more complicated than this. However, there are a number of problems with performing classification with this simple regression model that we've used. So it's basically just taking linear regression that we've taught, but instead of having sort of a continuous value for y, we've got 0 or 1, right, and then putting some threshold. And that kind of works in general, but it can have a number of problems as we scale up and get more complicated. So what we usually do instead is what we call logistic regression, right? In logistic regression, we sort of reframe the problem a little bit. One of the issues that we might have with something like linear regression is that we're not really trying to put the decision boundary in the middle of our points. As I kind of talked about and brushed over a bit, what we're actually trying to do is we're trying to put this decision boundary, or this point, such that the distance away from the line to these points is 1 and these points is 0. Ideally, what we'd like to do is we'd like to put this decision boundary such that the distance from the decision boundary to all of these points is as far as possible on one side, and the distance from this decision boundary to all of these points is as far as possible on the other side, right? We don't want it to be a distance or any specific distance away. We just want it kind of to be as far as possible away, right? And we've got 0 and 1 here, but our number line goes all the way up to infinity, positive infinity and negative infinity, right? So you can imagine that if we had some points that were potentially really far away, right, our model's trying to make this distance to this point equal to 0, so it's going to potentially pull this decision boundary right back here, right? So you can see if we've got a large spread of our groups, this can be a bit tricky for our model, especially if that spread is sort of asymmetric with one group. So what we want to do instead is we want to map that distance, negative infinity to infinity, to our distances 0 and 1. So we want to sort of stretch out our distance 0 and 1 to sort of infinity on either side, right? Because it's not really a point that we want to reach, but we just want to put this decision boundary sort of as far as possible away from the points on either side. A side note, if you're not aware, that minimum distance between our decision boundary and a data point is called the marginal, or the margin. It's the minimum distance, and we want that margin to be as large as possible. So basically, give us a large amount of wiggle room. Or, yeah. So how can we do this? What we do firstly is use what is called the sigmoid function. The sigmoid function, you may have seen it, looks like this. The important thing that it does though is it maps all of the real numbers to be between 0 and 1. So when the input is negative infinity, sigmoid maps it to a 0. When the value is positive infinity, it maps it to a 1. So what happens if we put this sigmoid function on the output of our model is that now if we regress from the output of the sigmoid and we try and move the output of the distance between our data point and that decision boundary, after the sigmoid, what we're doing before the sigmoid is pushing the distance from that decision boundary to our points to be as far as possible in the negative direction. Hopefully that makes sense, right? After this sigmoid, it's going to be distance 0, but the actual distance in the output of our model is going to be pushed further and further to negative infinity. The same is true for the positive case. If we're trying to push the distance after the sigmoid to 1, well, that involves pushing the distance from the actual raw output to positive infinity. And by using this on our output, we're trying to basically increase the distance, right, between our points in the decision boundary on either side. And again, we're not saying that I want it to be a fixed distance in the output of my model to 0 or 1. What I'm saying is that I want to push it as far as possible in either direction, or just to ensure that that distance is as far as possible. Okay. So that's a sort of a hand-wavy explanation without getting into too much detail. So we can actually put this sigmoid on the output of our model and train, and we'll do that in a second. However, there's a new problem that we introduced by using this sigmoid, and that is that the derivative of the sigmoid, remember we're going to be using gradient descent to train our model, and so we need to take the derivative of sigmoid and then use the chain rule to backpropagate that. The derivative of the sigmoid, as you can see, for very large values of the input, the derivative gets very, very flat. And for very, very large values, that derivative is very, very close to 0. What that potentially means is that if our model ever predicts a very incorrect value, right? So let's say that we have a data point that should be a 1. Let's say that the model outputs a very, very negative value, like a -10. Well, obviously we need to push that to a more positive value. But the problem is the derivative of the sigmoid is very, very flat for -10. So that's going to return us a very, very, very small derivative that we're then going to backpropagate, multiplying that value by the subsequent derivatives. What that means is that our model for that very incorrect value potentially won't train very much. We won't get any movement. And it could be the case where our model takes a very, very long time to train, right? And there's other considerations as well. That's the sort of main one that we're focus on. To sort of convince us that that is true, we can, like I said, put a sigmoid on the output of our model. So now that we've got the sigmoid on the output of our model, that decision boundary threshold actually changes to be 0. So the decision boundary is 0 before the sigmoid. So again, because we're trying to fit that distance 0 and 1 after the sigmoid, a distance of 0.5 after the sigmoid corresponds to an input of the sigmoid of 0. So 0 into the sigmoid, as you can see, gives us 0.5. So if I was to put the sigmoid on the output, I would need the threshold at 0.5. But if I just leave it off, because we don't need it during testing, I can just put that threshold at 0. So any positive values are 1, any negative values are 0, or positive greater than 0, let's say. So let's say any positive or greater, or greater than or equal to 0 is positive. You can put it for testing, but we don't need to, so I'm just going to leave it off. But we are going to put it on for training, right? Because our training, we're going to say it's going to be 0 or 1 after the sigmoid. So let's reinitialize. Remember to rerun your cells to reinitialize the value, the values of the parameters and the optimizer, and just double checking we've got all that right. Let's run it again. You can see before we had, I think it was 88.5, we've now got 79.25, so not quite as good. You can see we kind of get stuck here, converging, and then we seem to jump out of it and are slowly increasing again. So it could be the case where that very, very, very small derivatives, this is accuracy, you can see the loss here. The losses are sort of better indication of the training speed. And our loss is basically dropping much, 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 much slower than before, right? So we haven't actually converged yet. Maybe if we train for a bit longer, we would converge. Let's reinitialize and try another experiment. So we're doing, there we go. We have converged to the same value, but you can see it took much longer, to 10 times longer essentially. And that's probably because of that flatter derivative. Even if we aren't really far out, right? Even if we aren't all the way out here, you can see that even if we're operating around here, right, the derivative around 0 is about 1, but then it starts to drop over here. So even that small drop scales our gradients down a bit. Okay, so what do we do instead? Well, the simple solution is we just don't use a mean squared error. What we use instead is what's known as a cross entropy loss. And we're going to use a binary cross entropy loss here, but it's just a simplified version of our cross entropy loss. So our cross entropy loss looks like this. This is essentially obtained from the maximum log likelihood of a multinomial or a binomial in our case. Basically, it's the what you get from the maximum log likelihood of a binary distribution. So what we're doing instead of regressing to a distance value is we're kind of thinking instead of, for this input, what's the probability between 0 and 1 that this point belongs to a certain group? Or for the binary cases, what's the probability of it belonging to the positive case? Right, with our sigmoid, for multinomial cases, we tend to use a softmax rather than a sigmoid, but we'll get to that in a future lab. So that's the sort of hand-wavy explanation. Intuitively as well, the actual logs help us get rid of that really flat gradient. You can actually plug in your sigmoid equation into this and solve for the derivatives directly, and you can see you get a much nicer equation for the derivatives, but we're not going to get into that in this video. That's not what this video is about. But we're just going to introduce this cross entropy loss and see how we can sort of solve for this issue with the flat sigmoid derivatives and how we can do that with PyTorch. I've got a bit more information there, but I won't go over it. So the binary cross entropy loss is basically just a simplification of the cross entropy loss for a single case. You can simplify it a lot, assuming 0 or 1 for just one output. So we're going to use a BCE loss from PyTorch. BCE with Logistic loss basically assumes that the output of our model doesn't have the sigmoid. It incorporates the sigmoid into the actual loss function and simplifies it and make sure it remain numerical or maintain numerical stability. You can imagine if our values get very, very large at some point, our floating point variable can't contain such a large value, especially as we're trying to push the output of the sigmoid closer to 1, but 1 is at infinity, or negative infinity is at 0. So there's some checks to maintain numerical stability. So we don't need to put a sigmoid on the output of our model unless we want to get that probability value exactly, and then we need to put the sigmoid there. But very simply, all we're going to do is change from our MSE to a BCE with Logistic loss. Logistic just quickly, Logistic are the log odd probabilities. It's basically what you get for the inverse of a sigmoid. So the model gives us the inverse probability, or you invert the sigmoid, and then you put the sigmoid on the output to get back to the probability. But again, we won't go over that in too much detail. Again, we can threshold at 0 we don't have a sigmoid in the output of our model. If we put the sigmoid there, we'd have the threshold again. But the training loop is exactly the same, except we're now using BCE with logits loss. And you can see we converge to accuracy much quicker. You can see the loss still takes a little while to train, so you may need to adjust the actual value of the learning rate. But we don't have to train for 10 times as long. You can see we've converged much earlier on in any case. Okay, so this is all I wanted to go through in this video. It's just a very, very simple case of how we can use PyTorch's functionality to actually train on a very toy example, and also going over the basics of classification, using regression for classification and logistic regression as well. I have some resources in that Excel spreadsheet that I've linked on the GitHub repository if you want some more detail on logistic regression and cross entropy losses. Okay, so I'm going to leave it there, and I'll see you in the next one.